The first thing I'd like for you to consider is the square root of a product, something like this. The square root of 4 times 25. Now we know that this is the square root of 100, which is 10. But now I would like for you to consider the product of two square roots. So something like this. Okay, so this would mean the square root of 4, which is 2, times the square root of 25, which is 5, which is also 10. So we can see here that the square root of a product is equivalent to the product of square roots. Also, look at this, the cube root of a product, 8 times 27. This is the cube root of 216, which is 6. Now consider the product of cube roots. So the cube root of 8 times the cube root of 27. This would be 2 times 3, which is also 6. So once again, we see that the cube root of a product is equivalent to the product of cube roots. This is known as the product rule for radicals. The product rule basically says the nth root of the product of two numbers is equal to the product of their nth roots. Now you got to be careful. This does not apply to addition. Like for example, we cannot extend this to say that the square root of 9 plus 4 is equivalent to the square root of 9 plus the square root of 4. That's not true, because the left-hand side is the square root of 13, where the right-hand side is 3 plus 2, which is 5. The square root of 13 is not 5. So actually, let me put not equal to right here, all right? So this only works with multiplication, so be very, very careful. The square root of a sum is not equivalent to the sum of the square roots. All right, everybody, with the product rule now in tow, let us start simplifying some radical expressions. Now, the square root of 27, 27 is not a perfect square. So this is going to be irrational. Whenever you have a radicand that is not a perfect power of the index, in this case 27 is not a perfect square, then this is an irrational number. Now the way we're going to simplify the square root of 27 is by using the product rule. We're going to rewrite 27, which is the radicand, as a product of two factors, where one of the factors is a perfect square. Now we can rewrite 27 as 9 times 3, and the beautiful thing here is that 9 is a perfect square. Now I'm using the product rule to say that the square root of this product is equivalent to the product of those square roots. So then this just equals the square root of 9, which is 3, times the square root of 3. So this is the final evaluation for this expression. So the square root of 27 is equivalent to 3 root 3. 10 times root 75. Now, one thing is for sure, do not multiply the 10 and 75, but instead what we can do is we can rewrite the square root of 75 as a product of two factors where one of them is a perfect square. How about we do 25 times 3? Actually, let me go back here. Hold on, guys. What if I rewrote 75 as 15 times 5? 15 times 5 is 75 for sure. But the problem here is that neither 15 nor 5 are perfect squares. So instead of using that pair of factors, let's use 25 and 3 because 25 is a perfect square. All right, so we have 10 times the square root of 25 times the square root of 3. That's the product rule there. So this becomes 10 times the square root of 25, which is 5, times the square root of 3. So simplified, the answer will be, or the answer is, 50 root 3. Again, this is irrational. The reason why this is an irrational answer is because 75 is not a perfect square. The next one is the cube root of 72. All right, so the cube root of 72. 72 is not a perfect cube. If you list out some of your perfect cubes, you will not see 72 in that list. So the idea here is to rewrite 72 as a product of two factors. Now be careful, where one of the factors is a perfect cube. So you have to shift your thinking here. Don't think of perfect squares. Instead of think of perfect cubes. Now, you can rewrite 72 as 8 times 9. See, that's a good idea because 8 is a perfect cube, right? Now, let me just be clear. You can rewrite 72 a number of ways. So like the cube root of 24 times 3, or the cube root of, let's see, 18 times 4, I believe, and so forth. There's probably more. 36 times 2, right? 36 times 2. But the reason why none of these are good ways to rewrite 72 here is because neither 24 nor 3 are perfect cubes. Neither 18 nor 4 are perfect cubes. Neither 36 nor 2 are perfect cubes. So none of these are good ways to rewrite the radicand. We choose to rewrite the radicand as 8 times 9 because 8 is a perfect power of the index. It's a perfect cube. I hope that makes sense, right? So then the product rule says, well, this will be equivalent to the cube root of 8 times the cube root of 9, which is 2 times the cube root of 9. So you want to be really smart about, really clever about how you choose to rewrite the radicand. All right, now we have the opposite of the fourth root of 80. Opposite of the fourth root of 80. Now, we want to rewrite 80 as a product of two factors where one of them is a perfect fourth. Now, this is exactly why, guys, that in a previous lesson I was emphasizing the need for us to know our perfect squares, perfect cubes, perfect fourths, perfect fifths, maybe even a couple perfect sixths, so that we can do this kind of work, right? So here we go. 80 can be rewritten as 8 times 10. Wait a minute, that's not a good idea because neither 8 nor 10 are perfect fourths. I can rewrite 80 as 2 times 40. That's not a good idea because neither 2 nor 40 are perfect cubes. Perfect fourths. What would be a good idea here is 16 times 5 because 16 is a perfect fourth. All right, so keep that negative on the outside here. Use the product rule to rewrite this as the fourth root of 16 times the fourth root of 5. Okay, so then our final answer is the opposite of 2 times the fourth root of 5. Now this is fully simplified. All right, now let's simplify the following. The square root of x to the 11th power. Now watch this. The x to the 11th power means, now just bear with me, okay? It would mean x times 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 x, okay? I hope that was 11 of them. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we're good. That's what it means. Now watch this, everybody. What is your index? Your index is 2. You're right. This is a square root. So what I'm going to do is I'm going to group these factors so that each group is a perfect power of the index. In other words, because the index is 2, I'm going to be making groups of 2. If the index were 3, I would be making groups of 3. If the index were 4, I'd be making groups of 4, and so forth. So each one of these groups represents x squared, which is a perfect square, right? So then I can rewrite this as, now this is, the first group is the square root of x squared. The square root of x squared is, now actually let me do this for us. This represents x squared, this represents x squared, this represents x squared, this represents x squared, that represents x squared. So really, I'm going to do this piece by piece. The square root of x squared. The square root of x squared is just x times the square root of another x squared. That's another x times another x times another x times another x, right, everybody? That was the square root of x squared times 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 the square root of x squared. 5 of them. Now what is left inside? 1x all by itself, right? A little loner there. Now on the outside, notice that on the outside of the radical, you have x times x times x times x times x. Kind of lost track there. You have 5 of them. So in other words, x to the 5th power times the square root of x. All right, this is the final answer. This is the final simplification for this expression. Now, I want to show you a shorter way of thinking like this, all right? What basically this boiled down to is how many groups of the index can I make out of 11? How many groups of 2 can I make out of 11? Well, that's the same thing as the question, what is 11 divided by 2? Now, 11 divided by 2, 2 goes into 11 5 times, right? So then this is, let's see, if I can do this real quick, and then remainder 1, right, everybody? Now watch this. 5, the quotient, represents the power that's on the variable outside of the radical expression, and 1 represents the power that's on the variable inside the radical expression. So that's our quick little shortcut. I was using the shortcut in previous lessons, and I promised you that I would show you where that was coming from, and this is where it's coming from. From now on, whenever I am simplifying a radical expression with a variable with a power, all I will do is I will divide the power that's on the variable underneath the radical by the index, okay? The quotient will be the power that's on the variable outside the radical. The remainder will be the power that is on the variable underneath the radical. Now we have the square root of 125 x to the 7th power. The first thing I'm going to do is I'm going to use the product rule for radicals to rewrite this as the square root of 125 and then the square root of x to the 7th, okay? Now I'm going to continue using the product rule. The square root of 125, I want to rewrite that as the square root of 25 times 5. That's 125. And the reason why I'm splitting 125 up into these two particular factors is because 25 is a perfect square. Now, I have the square root of x to the 7th out here. All right, here we go. The square root of 25 is 5. The square root of 5 is just the square root of 5. Now, over here, the square root of x to the 7th, I will divide 7 by 2, right? And I could show you that off to the side. 7 divided by 2. Now, that is to say, 2 goes into 7 3 times. 2 times 3, of course, is 6 with a remainder of 1, right? Now, don't forget that that quotient of 3 represents the power on the variable outside the radical, and the remainder represents the power that's on the variable underneath the radical. So we're done. The only thing we have to do now is kind of clean this up. So this becomes 5 times x cubed times the square root of 5x, okay? So this is the simplification of that expression. Now we have 9 times the cube root of negative 54, x to the 11th power. All right, so here we go. So we have 9 times. I'm going to use the product rule for radicals to rewrite the radicand as, or the radical part of this term as the cube root of negative 54, and then times the cube root of x to the 11th power. All right, now I'm going to focus on rewriting negative 54 as a product of two factors where one of them is a perfect cube. So I'm going to rewrite it as negative 27 times 2. That's negative 54. Again, I want to emphasize the I feel like a broken record, but that's okay. I want to emphasize the need for us to know our perfect cubes and to know our perfect fourths and so forth. As far as the cube root of x to the 11th, that is the same thing as saying how many groups of 3 can I make out of 11? In other words, I'll divide 11 by 3. Okay? 11 divided by 3. So 3 goes into 11 3 times, of course. And 3 times 3, of course, is 9, leaving you with a remainder of 2. Okay? All right, so let's continue. So this is 9 times. Now the cube root of negative 27 is negative 3. And then this is, you know what I forgot right here, everybody? I don't know if you see it, but I forgot the index. This should not be written as a square root. This should be written as the cube root, right? Our index is 3. So let me rewrite this as the cube root of 2, like that. And then we can see that the quotient 3 represents the power that's on the variable outside of the radical. And then the remainder of 2, the remainder 2 represents the power that's on the variable inside the radical. So now that we're done here, all I'm going to do is simplify. So 9 times negative 3 is negative 27. You have an x cubed outside here, so I'll write that next to negative 27. And then inside the radical, you have the cube root of 2x squared. So this is the simplified answer for the original expression. All right, guys, we have the fourth root of a to the 8th times b to the 19th power. The first thing I'm going to do is I'm going to use the product rule to rewrite this as the fourth root of a to the 8th times the fourth root of b to the 19th. And then I'll use our shortcut here. I'll be dividing 8 by 4. I'll also be dividing 19 by 4, okay? So 8 by 4, I'm sure we don't, you don't have to show this if you don't want, right? If you don't need to. Of course, 4 goes into 8 twice. 4 times 2 is 8. Remainder 0, right? That's for a, okay? That's for the variable a. Let me make that look more like a 0. How about that? Okay, and then also divide 19 by 4. All right, 4 goes into 19 4 times. 4 times 4, of course, is 16. So then you have a remainder of 3. I wonder if I can fit that in there. Remainder of 3. Okay, so here we go. The quotient, remember, represents the power that's on the variable that is outside the radical, all right? So then I'm going to have a to the power of 2. And notice that 0 is the exponent for the variable that's underneath the radical. And so there will be no more a's underneath the radical because a to the 0th power is just 1. So that's it for that. For b, 4 is the exponent that's on the variable b that's outside the radical, like that. And then the variable that stays inside for b will have a power of 3. Okay, so this would be b cubed. All right, that problem's done. Good job. In this example, I am going to show you how you can use prime factorization to help you simplify an expression like the square root of 175. All right, so what I'm going to do first is I'm going to take the radicand, which is 175, and I'm going to create a factor tree, or use a factor tree rather, to help me generate the prime factorization for 175. So it might have have been a while since you've done a factor tree. Start with any two factors for 175, other than 1, of course. We can start with 5. You know that 5 is a factor of 175 simply because 175 ends in a 5. Remember, any number that ends in a 0 or a 5 will be divisible by 5. 5 times, let's see, 35 will be 175. Between these two factors, 5 is prime, 35 is not. So we rewrite 35 as 5 times 7. Now both 5 and 7 are prime, so I circle those. And so what we can do is rewrite the square root of 175 as the square root of 5 times 5 times 7. Okay? And now, what is your index? Your index is 2. So what I'll do is I'll group these factors in like factors in groups of 2, groups of the index. And so notice that this is basically the square root of 5 squared times the square root of 7. So I did two things at once. I used the product rule, and then I also rewrote 5 times 5 as 5 squared. So this is just 5 times the square root of 7. So this is how to use prime factorization and a factor tree to help you simplify. Let's do another one. The cube root of negative 384 times x to the 5th power. The first thing I'll do is I'll use the product rule to rewrite this as the cube root of negative 384 times the cube root of x to the 5th power. I could probably do even better than that, folks. I can rewrite this as the cube root of negative 1 times the cube root of positive 384 times the cube root of x to the 5th. Okay, so what I'm going to do right now off to the side is I am going to use a factor tree for 384 to rewrite it in a product as a product of prime factors. Now I know that 384 is divisible by 2 because 384 is even. So 9 goes into 38 19 times. Excuse me, I said that wrong. 2 goes into 38 19 times and then into 4 twice. Between these two numbers, or these two factors, 2 is prime, so I'll circle that. 2 is the only even prime number. And then 192 is again divisible by 2 because 192 is even. 2 goes into 19 9 times. And then 2 goes into 12 6 times. Okay, now 2 again is prime, 96 is not. 96 I know is 8 times 12. Let me rewrite that using yellow just to make sure that it's clear for everybody. 8 times 12, right? You can rewrite 96 as a product of any of its two factors. It doesn't have to be 8 times 12. It could be 2 times 48. It could be, a lot of different things. So it doesn't have to be 8 times 12. Neither 8 nor 12 are prime. 8 is, I guess I just want to be color coordinated, so just make sure everything stands out for you. 8 is 2 times 4, and 2 is prime, so I'll circle that. 4 is 2 times 2, and each of those 2's are prime. All right, now 12, let's go back to 12 here. 12 is 2 times 6. You could also do 3 times 4 if you'd like. 2 is prime, 6 is not. 6 is 2 times 3, and both of those are prime. All right, so the prime factorization for 384 is the cube root of, now let's count all these 2's, shall we? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then there's 1, 3. All right, everybody? Don't forget about the cube root of negative 1. We can evaluate this right now. The cube root of negative 1 is just negative 1. So I'll put a negative 1 on the outside. And then in just a second, I'll do this on the next line. I will evaluate the cube root of x to the 5th. I could have done it right there, but I was kind of running out of room on that line of work. All right, so I have a negative 1 on the outside, okay? And then what I'm going to do, folks, is I am going to group these factors here, prime factors, in groups of 3, in groups of the index. So make groups of 3, but you do want all the factors in that group to be the same. That's the best I can do, all right? So then this is really the cube root of 2 cubed. You have another one, the cube root of 2 cubed. And then you have the cube root of 6, right? Now, we're going to use our little trick here for the cube root of x to the 5th. Remember, and I'm going to do this part mentally, a little mental math here. 3 goes into 5 only one time. So that means I'll have x to the first power out here. And then when you divide 3 into 5, you have 2 as the remainder. So then you'll have x squared, x to the power of 2 on the inside, left inside the radical. I'm going to make my index look a little neater there. Make it look like a 3. There it is. All right, let's continue simplifying. I think we've done a good job so far. So we have a -1 on the outside, and then the cube root of 2 cubed. The cube root and the cubing power are inverse operations, so they cancel each other out. So that's just left, you're just left with a 2 times another 2 for this one here. The cube root of 6 is just the cube root of 6. It is what it is. And you have x on the outside and then a cube root of x squared. So the final answer can be rewritten as -4x. So 2 times 2 times -1 is -4. You have an x on the outside as well. And what stays inside is the cube root of 6x squared. All right? I hope you followed that example. That was a lot of fun. All right? So this is the final answer here. Oops, wow. I don't know what happened there. All right. There. All right, I have the 4th root of 162 x to the 5th times y to the 11th. It would be great if you would pause this video, pause the lesson, and try this on your own. Okay, I'm trusting that you tried this on your own. Maybe you did a factor tree for 162. You don't have to, but this is the way I'm teaching. 162 will be divisible by, let's see, 2 for sure, right? And 2 goes into 162 81 times. 2 is that prime number there. Now you could stop here because remember your index is 4 and 81 is a perfect 4th. I'm going to pretend like I didn't see that though, and I am going to continue. 81 is 9 times 9. 9 is not a prime number, so we're going to keep on going. So each of these 9s represent a pair of 3s. Now 3 is prime, so we are done with our factor tree. So going back to our problem, this can be rewritten as the 4th root of, now you have 2 times 3 to the 4th power. Or you can write it as 3 times 3 times 3 times 3 if you want. And then let's not forget the variables, x to the 5th, and then y to the 11th. Okay, I'll extend that radical a little bit. Now, here we go. We know that this 4th root and this 4th power cancel each other out, and so that 3 is on the outside like that. What stays on the inside of the radical as part of the radicand is the 2, right? So far, the 2 stays inside, but this 4th power and that 4th index here cancel each other out. 4 divides into 5 right here 1 time, so you have an x on the outside, excuse me, and then 4 divides into 11 twice, so then that represents y squared. All right, when you divide 4 into 5, your remainder is only 1, so just a 1x like that, x to the first power. And then when you divide 4 into 11 twice, right, your remainder is 3. So then you're going to have y to the power of 3 on the inside of the radical. So then this is your final answer for this problem. Isn't that great? This is using prime factorization. I'm a huge fan of it. Now, you and I have been using the product rule for radicals. There's also the quotient rule for radicals that says the following. The nth root of a quotient, a divided by b is a quotient. The nth root of a quotient of two numbers is equal to the quotient of their nth roots, like this. So let's use it for this example. Simplify the square root of 22 over 81x squared. Now, the quotient rule for radicals says that the square root of this quotient is equivalent to the quotient of the square roots, right? Like this. That's the quotient rule. And so the square root of 22 is just the square root of 22. That cannot be simplified because 22 does not have a factor. That's a perfect square. The denominator, however, the square root of 81x squared is just 9x. Okay, assuming that the variable x represents a positive number. So that's our answer. We're able to simplify this expression using the quotient rule. Let's do it again. We have the cube root of 5a squared over 8b to the 9th power. The quotient rule allows me to rewrite this as the cube root of the numerator divided by the cube root of the denominator. Now, the numerator is what it is. 5a squared, 5 is prime, right? So it's not going to have a factor that's a perfect cube. And then 3 doesn't divide into 2, right? 3 cannot be divided into 2. In other words, this numerator is already simplified. The denominator, however, the cube root of 8 is 2, and then 3 goes into 9 exactly 3 times, so that's just b cubed. All right, everybody, this is the quotient rule in action, okay? But I want to show you another way you can use the quotient rule. Watch this. We have the square root of 98 x squared y divided by the square root of 2y. Now, the quotient rule says that the quotient of these two square roots is equivalent to the square root of their quotient, right? So it's kind of basically going the other direction for the quotient rule. But anyway, what we see here is y divides out with y. And 2 goes into 98. What is that? 49 times, doesn't it? 49 times. So really, this turns out to just simply be the square root of 49 x squared, which is 7x. Look how nicely this expression looks pretty complicated, but it simplifies to just 7x. One more like this, we have the cube root of negative 375x to the 11th power divided by the cube root of 3x squared. Now the quotient rule for radicals allows me to rewrite this quotient of two cube roots as the cube root of the quotient of their quotients, right? Like that. Now the reason why this is really nice is because 3 goes into negative 175, exactly negative 125 times. So that works out really nicely. And then I can use the quotient rule for exponents to say that x to the 11th divided by x squared is just x to the power of 11 minus 2. That is to say x to the 9th power. Now this is great news because negative 125 is a perfect cube. The cube root of negative 125 is negative 5. And then 3 goes into 9 exactly 3 times. So the final answer is just negative 5x cubed. Isn't that nice? This complicated expression just simplified to negative 5x cubed.